Okay, everybody. Any questions? Anything? You'll get today homework 3, of course. We talked about homework 2, and we are back to linear programming today. So where were we with linear programming? You know, you have a set of half planes. 1, 2, 3, 4 half planes. We want to find the lowest point amount that is inside all these half planes. Or you want to determine that no such point exists and the feasible region, this intersection of all these half planes, the feasible region is empty and the problem doesn't have a solution. We looked at the history. A good time to mention that there is a linear time algorithm to solve the LP, and it's complicated. It's very hairy algorithm and very slow in practice, like slow to the level of it's theoretically exciting that you can solve this problem in linear time, but beside it, it's definitely not practical algorithm, as opposed to the algorithm that I'll show you today, that is very fast, very practical, and much simpler, and just needed this one little ingenious jump of observing why and how to arrange it to work. So we talked about the 2D linear programming, and the 2D linear programming said I need to just compute explicitly all the vertices of the intersection, all the vertices in the intersection of age I. You can write it as follow. I goes from 1 to n. You are used to this symbol being sigma. Just this is another symbol for intersection. It's just age 1 intersection age 2 intersection age 3, and age is a stand for half plane, right? And we didn't speak about it enough about lower bounds, but actually to find this intersection, you can show it's not simpler than the sorting the half planes. If I arrange these half planes, say along a parabola, take values from a parabola and ask what is the intersection, it needs a proof, but you'll see that I have to get all these half planes in a sorted order, which means that I cannot solve this problem in time better than omega of n log n, because to sort n numbers takes omega of n log n. You don't have a sorting algorithm that can sort any set of numbers in time better than n log n. It's a theorem that we will not prove in this class, but it's good that you'll know. You cannot sort an arbitrary set of n numbers in time better than n log n. In other words, you will show me an algorithm that sort numbers in, you'll claim that it's a very efficient algorithm, and I, because I'm such a nasty person, can find an input that will cause your algorithm to run in at least this time, maybe more. And you'll come up with a different algorithm, and maybe I'll come up with a different input. But for every algorithm, there is an input that, quote unquote, defeats it. At least defeats it to the level of no better than n log n. And of course, that's tight because, you know, you have 3 algorithms: quick sort, merge sort, and heap sort, that all takes order O of n log n. So that's as good as you can get. And then somebody should say, but what about radix and bucket sort, and don't you have ways to have sorting of numbers in linear time, like radix, for example? And The answer is yes, it runs in linear time, but it doesn't work for arbitrary numbers. You need the keys to be integers. They need to be only with a few decimal numbers. It's integer in a small range, and it's not arbitrary numbers. So what's the conclusion so far? That if I want to compute C exactly, or computing all the vertices in this intersection of hi in the feasible region, the intersection of hi takes omega of n log n, because you can sort. To solve it, you have to do something that involves sorting. You can get the data in a sorted way. And at this point, you are saying, didn't you promise us a linear time algorithm today? And didn't you cited the algorithm of Megiddo that runs in linear time as well, just 2 slides ago? And the answer is yes, you can solve linear programming in better time because you don't insist of finding all the vertices. I don't need to know all these vertices. I know what is my cost function, and this somehow implies that I can target my way in a more efficient way. So we said we can compute it in n log n by merge, by divide and conquer, and here is an order n square incremental algorithm. So we are doing an interesting step. We just had an n log n time algorithm, and now I am going to tell you about an n square time algorithm. How does it work? I'll start by computing the intersections of 2 half planes. I'll remind everybody what's a big problem, because we talked about other things at the meantime. To the LP input age 1 dot 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 age n, which are half planes, and C1, C2, or a vector C, which is a cost function, and the output find a point, let's call it x star and y star. The star or the asterisk here usually means that it's optimum solution. Which is inside all hi, comma, and minimizing C1x plus C2y. Or in vector notation, it would be vector C dot product, the vector x. Right? That's a linear programming notation. And each half plane, I just told you, I gave it as in the form, can give it in a few forms, but for example, alpha I x plus beta I y is small or equal than gamma I. That's my description of how do I tell you what is the half plane hi. I just had to specify 3 constants, alpha I, beta I, and gamma I. Every half plane you can write in this way with the corresponding alpha I, beta I, gamma I. Continue. Now I'm not going to do divide and conquer. Instead, I'm going to do incremental algorithm. I'll start by computing the intersection of two half planes. And now I'm going to add the half planes one by one. And at every moment, after inserting a half plane, I'm going to know what is the optimum solution to the problem, except that I don't require the optimum to be inside every edge I. I'll require it to be only inside the half planes that I inserted so far. Again, I'm going to insert a half planes and do something. Insert a half planes and do something. And the main tool to do something would be to solve a one-dimensional linear programming problem if needed. It will be clear very soon what is this if needed. So, what is a one-dimensional linear programming? We went through this slide, but I slightly modified it. So let's see what has happened. I told you somehow that I'm looking for a solution only on the line L. Again, I'm looking for a solution to the linear programming problem, which is what? I'm giving one line L. I'll ask what is the lowest point which is on L and is inside each one of the half planes h1 ... hn. And the algorithm is extremely simple. We saw it already. Let's refresh your memory. I'm going to divide the half planes. Is the font clear with everybody? It's a bit smaller than usual. Should I increase it? Nobody said anything. Readable by everybody? Okay. Okay. Okay, so I have the line L. I now split all the half planes into two groups. I'll assume general position assumption. I slightly insert, slightly rotate, slightly add a noise. So I will assume that I don't have a vertical half plane. No half plane is completely vertical, which means now that I can divide my half planes into ones that look upward and ones that looks downward. Formally, the one that looks downward contains the point x equals 0, x equals 0, and y equals minus infinity. That's a red set. Each one of them contains this point that is way, way, way down. If you'll go low enough, you'll be inside each one of the red half planes, and the other ones contain the point 0 and plus infinity. And I compute the point pi, which is L intersected Li. Li is a boundary of Hi. Remember this notation, it is as Cortas is in all this chapter. Pi is L intersected Li. So, and I'm concentrating first on the ones that looks upward, the purple ones. Here is one point. Here is another point. It's a plane that looks upward the time after. And what is the intersection of L with edge 1? The intersection of L with edge 1, it is a ray that starts at the intersection point and go all the way to infinity. Right? Here is L, maybe it's clearer. I look at this intersection point and said what I have is actually a ray. This is L intersection edge 1. Say if this is edge 1. And I'm doing the same thing with L intersected edge 2. That's the other intersection point. And the intersection point is where L crosses a boundary of edge 1. That is meets with the skin of edge 1 is a boundary of edge 1. This line is edge 1. Edge 1 is everything above this line. Okay, so I compute all these rays and all the intersection points, and which, if I'm looking for the intersection of all the half planes, in particular, I ask what is the intersection of L with each one of the half planes that are looking upward. Here is one such intersection point. Here is another such intersection point. If I'll continue these lines and somewhere down below, there will be another one. But what is the intersection? It determines by what? It determines by the highest point among all these point Li's that I computed. Right? Proof by example. Here is the intersection with P1. Here is the intersection with P1 is the intersection with H1. P star will be the intersection with H2. Both of them are looking upward. And what is the intersection of these two rays? It is just, of course, I need to be in all the half planes, in particularly, I need to be above the highest point of all these half planes, right? Because if I'm coming from infinity, I'm on the intersection of all the rays, and coming from infinity, I'm asking, as I'm falling, what is the first half plane that I hit? And that would be just the highest such intersection point. Similarly, so I'll specify, I'll call this point P star. And now I'm looking at all the half planes that looks downward. And what do I care about all of them? Doing analogous analysis, I'll compute their intersection points. Let's add another one. Here is another half plane, then I'll compute its intersection point with L. Remember, all of them are looking downward. All of them contain the point 0 and minus infinity. And which of all these points is important? It would be, of course, the lowest one. Because if I want to be inside all of them, walking from minus infinity along L, what is the first point that I'm hitting among the half planes looking downward. So this is an important point, this is an important point, and if I'm inside L, what is a feasible region? It starts here and it ends here. And if your cost function tells you look at the lowest point in general, that's a cost function that we like, try to minimize y, then you care about this point, the lowest one. If your cost function would be look at the highest point, maybe it is this intersection, but here is the intersection of all the half planes, provided that you must be on L, which I still didn't give you an excuse what's the importance of L. But notice that this algorithm also tells you something interesting. Another interesting data. Let's have yet another half plane that intersect all of them and look downward. Here is another actually in this picture it will be easier to add another half plane that looks upward. Here is age 17 and it looks upward. So the lowermost point of all the intersections that looks upward will be this. It is not this. Once I inserted this purple guy, it says the intersection of all the half planes looking upward will be this point. This is the lowermost point. And what can I conclude from this example? So what is the optimum point? There is no feasible solution. If you must be on L, then you cannot both be below this point but above this point. They are disjoint. Let's have a simpler scheme to it. If this is L and I have one constraint that forces me to be on the lower part below this point, and at the same time on the upper part above this point, then there is no intersection between them, and at this point it will be my good timing to go to the user and says, hey, there is no solution to your linear programming, at least not if it must be on L itself. Okay, so this algorithm, the one-dimensional linear programming, 1DLP, takes a line L, takes a set of half planes h1 ... hn, and either finds the optimum of the cost function on L and inside each one of the hi, or tells you there is no intersection point. Okay, and we are going to use it as a subroutine in our next code. Notation. I'm going to do the incremental algorithm. Remember, I'm going to insert the half planes one after the other. Insert, I'll start where I say computed the intersection of h1 and h2. That's where I start, and then I'm inserting h3, inserting h4, inserting some other half planes. Maybe later I'll insert h5 that you just see a shadow of it right now, but at the meantime some notation. So hi is the ith half planes. Right? So for the time being, I'm thinking about this algorithm. Incremental algorithm is like a streaming algorithm. Somebody broadcasts to you each one of the hi and in order, and each moment you solve the problem of what is the solution to the linear programming given the half planes that I have at the moment. And then you're receiving another half plane and another half plane and another half plane. And each time you're updating your solution to the linear programming. So, notation. Age I is a ith half plane that I'm going to insert. Age 1, age 2, dot, 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 age n. Li is a line that bounding age I, the border of age I. Just notation. Ci is a feasible region at the ith step. Ci is a feasible region at the ith step, that is after I inserted all the first I half planes. So Ci is, sorry for the font, Ci is age 1 intersection with age 2 intersected with all the way up to, and I stop at age I. The font is small. Ci is age 1 intersection age 2 intersection dot dot dot. Intersection age I. That is, I'm stopping at the I step, and Vi is the optimum vertex in Ci. We saw like 2 weeks ago that the solution to the linear programming is always at a vertex, and Vi will be the optimum solution to the linear programming given all the first I half planes. So if this is age 1 and age 2, this vertex will be V2. C2 is this wedge, everything above these two lines. Please help me, please. What is V3 in this on the whiteboard? What is V3? It will be exactly the same as V2, because even when I'm inserting age 3, V2 is completely happy to be inside age 3. If it's not broken, don't fix it. If you have a solution to some sub-problem, and then you're adding more constraints, but they don't violate the optimum to the solution, then obviously I cannot get any better than V2, because that's age 1 and age 2 already bounce me, and V2 doesn't contradict age 3. It is inside age 3. It's a diet that gives you enough of vitamin 3, if you remember the example we started with. So this is also V3, and this is also C3. This intersection would be C3. And a warning, I will speak about the feasible region at the I step. I never bother computing all the vertices of this intersection. Again, I can speak about it as a concept. The algorithm does not compute what is this intersection. Okay, what will be age 4? Sorry, V4. This is age 4. What is V4? Same guy. Because age 4 does not violate age 1 and age 2. Okay, the same goes in our little graph. What? That is, this point will be V2. I always start with 2 half planes. So this wedge will be C3. And now I'm adding age 3. Now I'll add age 5 in our case. Here is age 5. What is now V5? it cannot be v2 because v2 is not inside age 5. There is a violation. It's always, the objective function is always going down. I mean, the algorithm will work, the algorithm doesn't need this assumption, it's just for us to visualize it. That the algorithm always have what's this direction, C1, C2. If you think about these two constants, C1 and C2, and we are trying to minimize x times C1 plus y times C2, then we can think about C1 and C2 as a direction of the cost function, as a vector that points somewhere, and if we want it to be look downward, then C1 will be 0 and C2 will be -1. I'm trying to if I'm trying to maximize C1. If I'm trying to minimize, I'm going to the other direction. So just for convenience, I'll assume that the gravity pulls me downward. So in this example, it will be the new optimum solution will be this vertex, and I need to find it somewhere. Right? The intersection will be this vertex. You have to be above age 5, and at the same time you have to be inside all the half planes that you were in before. It's incremental. They are not age 1, age 2, age 3, age 4 are not going anywhere still. So in the slide, when I'm inserting age 3, that would be V2. Here I'm inserting the third vertex, and V3 is becoming this point. Okay, everybody is good with this notation. The heart of the algorithm, and it's algorithms that had so many follow-ups works that use the same ingenious principle, that a lot of the algorithms now are using randomized incremental, but at the main time it's only incremental. I'm inserting the half planes. So the notation is clear to everybody. Age I, the ith half planes. We always have the intersection of age 1 intersected age 2 intersecting all the way up to age I. I don't know anything about age I plus 1, age I plus 2, etc. Don't care yet. And Vi will always be the optimum solution of the cost function that is inside the feasible region Ci. Define the intersection of the first I half planes. This is Ci. Okay, don't forget it. Okay, and this is a very simple, very easy theorem, but it also translates almost word by word into an algorithm. So assuming that we are at the ith step of the algorithm, I'm going to insert, here is the solution of Vi minus 1. That is, I know what was the optimum solution of all the half planes that I inserted so far. Remember, the other half planes creates a polygon. Maybe I know about some of its vertices. Not necessarily. I don't necessarily keep track of other vertices. I only keep track of the vertex that led to the best solution so far. So here is Vi minus 1, and I'm about to insert age I, sorry. I'm going to insert age I, the ith half planes, and I'm asking what happens to what is the difference between Vi, the solution after inserting age I, versus the previous solution Vi minus 1. So if Vi minus 1 is inside age I, that was the case over here when I inserted age 3, then if vi minus 1 was the optimum before, and now you're adding a constraint, but this new constraint doesn't violate vi minus 1, well, you cannot get any better than vi minus 1, and you cannot get anywhere below vi minus 1, and you cannot get, and you will definitely don't want to get worse. Adding more constraints can only damage your cost function, your achievement so far. So if you don't need to change it, you just inserted this red guy. It used to be age 3. You have just inserted age 3. It didn't violate v2. v2 was the optimum so far. Then what should I do? I will just say that the new optimum, vi, is just the old optimum, vi minus 1. Make sense? The previous optimum is still the old optimum. I can move now to the next half plane. How much time did it take me, even though we didn't, it takes to realize that this point, let's call it xy, that's a point of v2. And now what do I do when you show me age 3? Remember age 3, like every other plane, age 3 is written as some constant alpha 3x plus beta 3y is smaller or equal than gamma 3. So all my checking is just take xy of v2, place them as x and y, and ask, is this violating gamma 3? If it's above gamma 3, if the result is more than gamma 3, then it's not inside the half planes. Because in this way that I write it, if I replace it with an equal sign, then I define the line of h3 with this small or equal. It refers to the one side of this line. So checking if a point is inside the half plane, that's very easy. It takes constant time. So that's if we are lucky. If we are we add a half planes and we don't need to work at all, we just need to validate that the previous solution is the current solution. And then I can move to the next step. What happened if vi minus 1 is not inside age I? Sorry, that's a case of age I that doesn't violate, so I don't need to change anything. Here is another case that I don't need to change anything. My half planes is actually from the other side, but still vi minus 1 doesn't violate it. Let's think about this case. Here, vi minus 1 is definitely not inside age I. Then I need to find a new optimum solution. I need to update what is vi. It will not be vi minus 1 because vi minus 1 violates age I. You now have a different type of vitamin, and and your old diet doesn't satisfy enough of this new vitamin. Then I need to solve a new linear programming problem. I have all the constraints that I had so far. And I cannot use them directly because I need to find a solution for a new linear programming. What is the best point inside what is the best point that satisfies all the ith constraints, including age I? But here is where a very simple observation makes the problem way, way faster, way easier. But it's really sharp observation. If vi minus 1 is not in age I, then possibly you don't have a solution at all. Possibly there is no solution at all because the feasible region is empty. However, if there is a solution, then of course Ci equals Ci minus 1 intersection with age I. That's just a definition of what is Ci, the intersection of everybody. But that's the heart of the algorithm. Now you still have two-dimensional half planes, but Vi, the new optimum solution, you can limit your search only to the line Li. Vi will not be floating somewhere in space. It must be on the line that bounds age I. Very simple, but very deep. Right? I had the old new solution before I inserted age 5. And now you insert age 5, you realize that the V2 or V3, V4 are not inside age 5, the green guy. Then you still need to compute what is V5. You still need to solve linear programming problem, but it's linear programming problem in one dimension, not in two dimensions. Because the new optimum solution, we will have to prove it, must be on the green line. In general, if you just show me a half plane, then I don't know which of the half planes determines the optimum solution. But here, because I had a violation, it is an indication that your next search is easier. You don't need to look for V5 floating in the space. You can start by assuming that the new optimum solution will be on the line. And then you can solve it using a call to the one-dimensional linear programming. In the 1D linear programming that we had 2 slides ago, we assume that there is a line that tells us only look for a solution on this line. So let's prove this theorem. Right? Case 1 is trivial. If Vi is on age I, then you don't need to fix it. Vi minus 1 is just Vi. And so what we need to prove is a second case, that Vi will lie on the line Li, the line that bounds age I, if there was a violation. So assume not. Assume that Vi is not on the line Li. Assume by contradiction that this is V5. That's the optimum solution that satisfies age 5, this green guy. And what you're going to do is to draw a segment that will start at V5 as one endpoint. V5, notice it's not on age 5. Question, is V5 satisfies age 1? Is V5 is a solution. V5 is a solution to the problem of minimize y such that xy is inside age 1 and also inside age 2 all the way up to age 5. Age 5 is the last half plane that I inserted. So V5 by definition must be inside age 1. It must be inside age 2, it must be inside age 3, all the half planes that I solved so far, because I said that it's the optimum solution to the ith problem. Okay, what about V2? It's inside all the half planes, excluding age 5. It used to be the optimum solution so far. This is V4. Let's clean it a bit. This is V4, so in particular it is inside age 1, age 2, age 3, age 4, but not inside age 5. I know that it's not inside H5 because I said that that's a case that we are handling in case that the old solution is not inside the last half plane that we added. So V4 is only inside, sorry? V4 is, I'm in my house. Uh, okay, yeah, all humans. And I should have, I think that as a host, but I need to remember how. I think that he'll get to Broadway in a second and we'll solve it. Maybe not. Okay, I remember. I'm going to participate and need to go to participate. Yeah, participate. Mm. And who is? Okay. So this is V4, this is V5, and let's draw a segment that connects them. Now, remember our cost function is linear function. Linear function meaning that, let's ask you a question. But I need an answer within 20 seconds from the moment I finish the question. Okay? I need an answer within 20 seconds from the moment that I'll tell you go. This is the Earth. I put a rope around the equator. That is a rope, the length is about 40,000 kilometers. It's around the equator, that's the perimeter. And it's just snagged to the equator. And the Earth is a perfect sphere. And now I'm adding 6 feet to this rope. So now this rope has some slack in it. I arrange it concentric. So now with the 6 more feet to this rope, I can pull it to all the sides. So now there is some gap between the equator and this rope. Can a cat walk underneath this gap? The equator, you know, is a metal band that surrounds the Earth, and it's a perfect circle. I put a rope around it, snag the rope, add 6 meters, arrange it concentric around the Earth, and I'm asking in the gap that I generated here, can a cat walk or not? Remember, perimeter was 40 kilometers to start with, and I only added 6 feet, 2 meters. Okay. Mhm. And that was exactly my answer when I was asked this question. What is a function that correlates the perimeter of the radius to the perimeter? The radius to the perimeter of the Earth. What is a function that correlates them? The perimeter equals pi times the 2 pi times the radius, which means that this function is linear. So if the size, so what did I do? I took some original radius, the radius of the Earth before, and I added some delta x, or delta r, delta to the radius, and I'm looking at the gap that I'm getting with the new radius. Or I look at the old perimeter and I look at the new perimeter. This delta y over here. If the Earth was of, if I would replace the Earth with a basketball, then most of you will say that probably yes, because they're of the same order of magnitude. So if I'm asking what is a delta x and delta y when the radius is very small, everybody would say that yes, there is enough room. But now I'm asking what is a delta before and after, but when r is much larger, and our collective intuition, I think, is saying no, because this is so large and this is so small. But the answer is that absolutely yes. It's just as if you got exactly the same gap as if you were speaking about a basketball or tennis ball or an atom. Correct? And if you actually put it in the equation, you realize that there is about 6 feet divided by 2 pi, which gives you about a feet, which is feet for pretty large cats. But the important thing is that if you're moving one step in some direction and you get some profit, that if you'll continue to move in the same direction, to increase the x or to decrease the y, you'll keep getting profit. And the amount of profit that you'll get will continue monotonically and in the same rate. Delta x and delta y are fixed no matter where you are. Let's get back to our problem. If this is V5, that's the optimum of the first 5 half planes, and my cost function tells me to go downward. Since V5 is floating somewhere in the air, inside all the half planes, what happened to my cost function as I'm walking along the segment? Again, what happened to my profit? I think the cost of the diet when I'm following my way from V5 to V4, especially if my cost function is just go downward. As you're walking along the segment, you just improve your cost function. Everybody agrees? If it worked for small part, and here V5 is not on the boundary of any half plane, then walking more and more will just make your cost function better and better. Your cost function here is to go as low as possible. Which implies what? This point is inside, V4 is inside V4 lies, for example, in H3, but so is V5 lies inside H3 as well. What do we know about convexity? If I have 2 points that are inside a convex set, the whole segment of them is inside the convex set. Definition of convexity. If you have 2 endpoints inside the half plane, the whole segment between them is inside the half plane. V4 is inside H3. Actually, they are all inside H1 as well, and H2 and H3 and H4. That's true to all of them, except H5 was a guy that I inserted, and because of H5 I had to go to a new optimum. So as I'm walking down the segment, what is happening? My cost function is getting better and better. I don't hit the boundary of H1, nor of H2, nor of H3, nor of H4, because both endpoints that I have are inside H1 and 2, H3, and 4. However, this point is inside H5 for sure, and this point is outside H5 for sure, because we checked our function and we ask H5, are you contradicting V4? Can I keep using the same optimum? And H5 says no. V4 violates H5, meaning that as I'm walking along a segment, I will have to exit H5, and once I exit, I cannot go back again into H5, right? It's convex. It's a plane. Conclusion: the new optimum solution cannot be flowing in the air, but it must be on H5. That is, I don't know that this is the optimum solution. Don't misunderstand me. I don't say that this is the optimum solution, but I definitely say that this is not the optimum, because as I go down, I am getting better and better. So what did we contradict? We contradict the assumption that we are not on the boundary of H5. We contradicted we contradicted this point is better than V5, and is legit. It satisfies all the half planes. So what did it contradict? Our claim that our new optimum solution V5 is not on L5. Contradicting the assumption that the V5 is not on L5. So it's really cool. It's really cool theorem. Let's get a bit less blur. It's really cool and really powerful theorem. You have it all in the slide as well, because it means two things. It means you can look at your new optimum solution only on L5, only on the line L5, so you can call the one-dimensional linear programming. But going back to the theorem, it has another meaning. If you cannot find a solution on L5, if you cannot find a solution of L5, because we had this case that we had some remember, in the 1DLP, we had this, then we called it L, now it's becoming L5, and we had some half planes that say your solution must be above all these points, and half plane that says your solution must be below all these points, and there is no intersection. So what this theorem actually tells you is that if you fail to find a solution of L5, it means that there is no solution at all. It means that there is no solution to the 2D linear programming, to the two-dimensional linear programming. Because if there was a solution, since you violated, since V4 was not on H5, then the new solution must be on the line that bounds H5. And if you cannot find a solution on this line, then there is no solution at all, which exactly said that Ci, the intersection of all the 5 half planes until this point, is empty. And you should stop the linear programming. There is just no solution. Very good. So that was a big heart of the algorithm. So we moved from a two-dimensional linear programming into one-dimensional linear programming, and promo to what we'll discuss in the future, we can move in a similar way from three-dimensional linear programming into two-dimensional linear programming, and from 4 into 3 and so on. Okay, you have the same proof once again, assuming that V5 or Vi is not a Vi minus 1. So then the solution must be on the line that bounds age 5, because if it's not on this line, then you can continuously move from the solution into from Vi into Vi minus 1. Your cost function will get better and better. You are still inside all the constraints that you had so far, except age 5, age I itself. So it contradicts, and this point has better cost functions than this point. Okay, and so just explained how to do the one-dimensional linear programming. It's you had it in a better way in the figure, but I didn't want to remove this slide. How much time does it take to solve the one-dimensional linear programming, finding all these intersection points and see what is the highest, what is the lowest among all the max and all the mean? How much time does it take? Well, it's order n, but to be more precise, it's the ice step, it takes order of I. It's linear in I, in the number of half planes that I had so far. Remember, I don't know yet about age I plus 1, age I plus 2, and so on. So how much time can the algorithm take? Here is age 1, here is age 2. This is V2. Here is age 3, age 4, age 5, age 6. This is V2. V2 violates age 3, so when I'm inserting V3, I need to solve the one-dimensional linear programming on the line L3. So here is V3. But I did spend linear work in the number of half planes that I had so far. I'm inserting age 4, V4, the way that I arrange my half planes, they keep contradicting the previous solution. I have to call this procedure, every time that I'm inserting a new half plane, I have to call the procedure that solves the one-dimensional linear programming on everything that I had so far. So the overall running time is some constant times 3 when I had 3 constraints, plus 4 when I had 4 constraints, when I inserted the fourth number, 5 when I'm getting to the 5 half planes, all the way up to the last half planes that I'm inserted. Each one of them violates the previous solution, and I have to call the one DLP for each one of them, which brings me to the fascinated running time of order of n squared, which is significantly worse than the n log n solution that I just had earlier. Okay, everybody agrees with this solution? If I'm solving the problem, if I'm inserting the half planes in this order, then I'm spending linear time. Can you think about another order of inserting the half planes that will cause the same algorithm to run in a better time? For the examples that you see on the board. I claim that if you'll change the order of insertion in the examples that you see on the board, it will run in linear time. But what is a different order? Let's call this one age 1. and let's say that, and this will be the new age 2, and this will be v2, that's where I started from, and now this half length will be the new age 3, which does not violate v2. So I'm just spending time to check that there is no violation, but this is also becoming v3. And this is a new h4. Actually, it was h4 before. This is a new h4. It doesn't violate v2. Perfect. No violation. So I'm just, for every future half length, I don't spend any time. So if I would know the order ahead of time, I can save myself a lot of time, which is just the case of if I know the solution, then I know the algorithm that finds the solution. I mean, that's the whole problem. What's the right order? But at least you see that the order really affects the running time. So remember our example with the maximum. Let's think about the one-dimensional linear programming. I'm on a line and I'm inserting one-dimensional constraints, call them age 1, age 2, age 3, age 4, age 5, but I'm inserting them at some random order. These are all values age 5, or called it y5, just the y value. I'm only solving the problem in the 1D. We had it as a discussion, it's not on the slide. And we said that what I'm keeping is a minimum. Well, in the example, it was a maximum. Doesn't matter. I'm keeping the minimum of all of them. I need to be above all these numbers. And what happened when I'm inserting them at a random order? We said at the ith step, when inserting age I, again, for this one-dimensional problem, what did we say? What was the probability if they are inserted in a random order? Tell you, these are the constraints, but at which order I actually insert them is not necessarily this one, but a random order. What did we say? What is the probability that vi is not vi minus 1? Let's take a slightly simpler example. Right? I'm asking what the probability is that the old solution, that the solution for vi is different than the solution vi minus 1. That is, that I need to update m in the previous example where I kept the maximum. And I'm saying, let's take an even simpler solution. I insert two half planes, only age 1 and age 2. In this example, only age 1 and age 2, the solution must be on this line. It's one-dimensional problem. And I'm asking what is the probability that v2 is not v1 if I take a random permutation of these two guys. And what was the trick over there? The trick was to say, among these two, one of them is special. The one that is pointing upward, the maximum of these two is a special. What's the chance that a random permutation will insert first age 2 and then age 1? Since all permutations are equally likely, there is the chance that this is inserted before this is exactly the chance that this is inserted before this. The special, the maximum one is likely to be the first one that I insert or the second one that I insert, and it's completely the same part. So the probability that v2 is not v1 was half. And that's called backward analysis. It's the idea that we're already inserting them, and then I'm picking one and pick one of them at random, and I remove it. That is moving backward in time. I pick one of them and I remove it at random. What's the chance that the one that I picked will be the maximum if each one of them has the same chance? If there are two, the probability is half. If there are I, the probability will be 1 over I. Right? There are I half planes. One of them is going to be removed, just backward the time. One of them would be the last one to be inserted, implying that if I move backward in time, one of them at random will be removed. So as you can guess, and that's promo for the future, that just shows the nth cube. As you guess, what we are going to do next is to say, let's insert them, but at a random order. Let's insert them, but at a random order. We'll insert them, we'll first permute the array that contains these half planes, and only then we insert them. And and then I'll ask the same question. What is the probability that Vi is not Vi minus 1? If Vi is not Vi minus 1, then I need to spend linear time to fix the problem, to call the one-dimensional linear programming. But let's look at the solution for the first I half planes. Some of them is the first I half planes. I'll finish in 30 seconds. And I'm saying, what is the probability that the last half plane that I added caused the problem, that Vi minus 1 is not Vi? Well, if the last half plane change the optimum solution, if edge I caused the problem, then edge I must be, the new solution must be on the line bounding Vi. Right? If I violate something, at least the new solution is on my boundary. So when I look at this picture, if I had a violation at the ith step, then I am one of the half planes that defines Vi. How many half planes defines Vi? In the one-dimensional problem, I had only one. Two-dimensional problem, to define what is Vi, I need two half planes that are the bad guys. Both of them are the two special ones. So this will be special and this will be special, but being a special has nothing to do with the order that I pick. So I'm asking, let's assume that I already inserted all the half planes. When I inserted the first I half planes, this is the shape that I'm getting. Here is the optimum, the lowest point in the shapes that I'm getting, and now I'm doing backward analysis. I pick one of them and I remove it. What's the chance that the one that I removed is actually touching Vi? But the chance that the one that I removed is actually contains Vi on its boundary, given that there are I of them. Two are special, but the permutation doesn't care about are you special or not. The permutation just said one of them will be the last one to be added, or one of them will be, when I'm switching time to move backward, one of them will be the first one to be removed. What's the chance that if I have I half length, what is the probability that the one that I removed actually contains Vi on its boundary? And the answer is, of course, it's not 1 over I. Somebody needs to spit it out so I can go home. You have you have to, one of Vi is determined by two half planes. Vi lies on the boundary of two half planes. It lies on the one half plane. Here are my I half planes. This is the lowermost point, and this would be one of the special half planes. And here is the other half planes. Let's call them H prime and H double prime. These are the two special ones. Why are they special? Because they define the optimum, but it doesn't matter what makes them special. When you look at all the I of them, you can point out, here are the two special ones. This one and this one are the two special ones. But it has nothing to do with the way that I picked the that I pick the order of insertion or the order of deletion. Every order is equally likely. So you inserted them in some random order, or now moving backward in time, you remove them at a random order, you pick one of them to be removed. What is the chance that the one that you removed is one of the two green ones? Because that, I'm sorry? The probability that Vi is not Vi minus 1, that's the hard and the ingenious part of the algorithm, is just the chance that the one that you are removing now caused Vi to change. And then Vi must lie on it, which is exactly 2 over I. That's a chance that Vi minus 1 is different than Vi. So what is the expected work at this stage of the algorithm? If Vi is different than Vi minus 1, then I need to call the one-dimensional linear programming. The one-dimensional linear programming runs in time C constant times I. That's a 1D LP. But I don't always have to call it. Actually, the probability that I need to call it is 2 over I, because there are only two special ones. So repeating the algorithm 1,000 times, what is the expected work at the i's step? What is the average if you repeat the same experiment billion times but picking a new permutation at each time? The expected work that you are spending is asking, you're spending time which is constant times I, but you're doing it only with probability of 2 over I. So on average, how much work did you spend in the i's step? 3 times I. It's a constant. The expected work is only constant. That is, the larger I is, the more work you need to spend if you're in bad karma and you need to update Vi. But the larger I is, the smaller the probability that you need to go through this process. There is a higher chance that Vi minus 1 is the same as Vi, and then you just need to check it, say there is no violation and I don't need to do anything. We'll go through it in the next class, but yeah, that's essentially the whole idea. The idea that if you have a new optimal solution, if there was violation at the I step, then the new solution is on the then the new solution is on Li, on the boundary of Vi, and the argument that the probability that it happens is only 2 over I. Very, very simple when you see it. To get to it, well, I don't know, many years of research, people were struggling with linear programming and nobody saw it. And yeah, and we'll see it a few times in this course. Thanks, everybody. Questions?